time we finished with the lemma, which essentially shows that we have something in FK model which is discrete analytic. So once again, the setup was that we have some domain like that with boundary conditions, and we do FK model for Q equal 2. So we can do it right as loops. And we introduce boundary conditions so that beside loops there is a curve which runs from one end to another. Well, and besides there are a number of loops. And then we define the function. So it's points A and B. Function f of z is the expectation that we passed through this point z, but taken with a weight which is basically counts how many turns we made. So the weight is lambda to the power number of turns of gamma from B to Z. Well, it doesn't really matter which side we count, but we decided to count on the right side, so it's from here to here. So on this specific picture we made one right turn, and then the lemma was that for Q equal 2, if we take lambda e to the power minus I pi over 4, so it's, well, this is lambda, so it's square root of minus I. Then we have a property that for any four neighboring edges, let's say label them north, south, west, and east, f of north plus f of south is equal to f of west plus f of east. And moreover, this actually gives more information, because if we do start doing our domain, then so that was say lemma 1 and lemma 2, or just an observation we made, that the argument of f is fixed on every edge up to pi k. So basically here, if here y f is real, so I'll just write numbers to which f is proportional. So here f is real, here f is imaginary, here f is real, here f is imaginary, here f is real, here imaginary. And basically the thing once again is that when we travel we always have black on the left, so when we arrive here we can only arrive from one side, so we make some round number of turns, and each turn, well, if this has weight 1, then basically so one, this will have minus 1, weight minus 1, so it won't change the argument by well, it might change argument only by pi. And on the other edges it's lambda inverse, lambda inverse, lambda. So for example, this essentially means that so for example, if we take this point, then we have real and imaginary number which give us some real and imaginary number which give us a sum which is proportional to lambda and lambda inverse. So this is lambda inverse. And that means we just write the same complex number. So we put it, let's say this is point u. So we define f of u like that. And then just f of u is written in a basis real part and imaginary part here, and proportional to lambda inverse there. Well, in particular, it means that if we know these two numbers, we know two coordinates, then we can get those two numbers. So f north projection on this vector will be just sum of these two divided by square root of 2. Projection on this will be difference of these two divided by square root of 2. But also, if you know these two numbers, you can get the other two. So if you have a vector and you know projections on any two lines, you can get the other two projections, and there will be some linear function. So in a sense, we have two, this is not one relation, but two relations at this vertex, because it's a complex relation, so it has real and imaginary part, but the functions are effectively real. Okay. So now the question is that, so there was an exercise that you can get the actual, for this function you can get the actual Cauchy-Riemann equations, and there are two ways to do it. Either you take the function as defined at u, and then you would have Cauchy-Riemann equation like that this difference is equal to that difference times I, or you can get Cauchy-Riemann equation, say, on real or in imaginary parts on horizontal edges. So we know that the function is analytic, and if we have a function which is analytic inside the domain, discrete analytic in this case, to reconstruct it uniquely, we need to know the boundary values. So the question is, what can we say about the boundary values? So let's start with an observation. So observation. So we'll start first with a sort of informal thing. So how does, so suppose we have some domain omega, we have this point A, we have this point B, and suppose that point Z belongs to boundary of omega, say, somewhere here. Then essentially, when we arrive by our interface to this point, it will have the same number of terms as if we follow the boundary. So the same number of terms as the tangent vector makes. So the winding of gamma from B to Z is the same as the winding of, let's say, boundary of omega from B to Z. So I have to be a bit strict, how do you say it, because gamma starts orthogonally to the boundary, and the tangent vector is tangent, so maybe one has to add here pi over 2 or something, but to be completely rigorous. And now, what do we do when we turn by some angle, by angle 90 degrees, which each time we put a factor of lambda? So it's let's say what we had turned by plus 90 degrees. So turned by plus 90 degrees, it's what? If we just look at the tangent vector, so that is tangent is multiplied by I, and weight in our case is multiplied by lambda, and lambda is square root of minus I, so it's 1 over square root of I. So basically, if we will follow the boundary, so on the boundary of omega, f will always be parallel to 1 over the square root of the tangent vector. Well, if it is at this point, if we put constant in front that it's this point is parallel, so because whenever we turn where the boundary turns by I, we multiply weight in f by 1 over square root of I, and the tangent vector is also multiplied by exactly that. So just when we'll go along the boundary, if tangent vector is turned by I, then the weight is turned by 1 over square root of I. So f always stays parallel to 1 over square root of tangent vector. And this holds when we go along the boundary, but if we go by other route, we have the same winding. So it always holds. So I can write it informally is that f is parallel to 1 over square root of dz, or f times square root of dz is parallel to 1, is real. Or imaginary, depends how we start at the beginning at the point, how we define in the first point f to be 1 or I. Or we can square it and write that f squared dz is real. Or if we integrate, well, now it's well, okay, we can write that this is constant. Well, again, it's real. So if we started with some real number, so basically, it means that, like informally, that if we put h to be integral of f squared dz, then on two arcs, on arc AB and on arc BA, when we integrate f squared dz, we get real numbers. So imaginary part of h is constant. And better yet, I put just h to be equal imaginary part of this integral. And then h is constant on these two arcs. Because this integral is purely real, so imaginary part is 0.
H is defined on the boundary.
Well, I mean, it's not, well, I mean, it's defined, it's informal, so we haven't defined it yet. So we have a discrete function f, and we try to see what we want to do. So we have a discrete function f, which is discrete analytic in the usual sense if we restrict to vertices, and for which informally on the boundary we can say that f is parallel to 1 over square root of tangent vector. Yeah, maybe it's, let me do a simple remark here, so in the middle of the observation. So such problem that f is parallel to 1 over square root of tangent vector, or any problem, or more general f parallel to some function phi of z, is called the Riemann boundary value problem. Boundary value problem. Riemann got this problem in the study of tides. So he has a famous paper about the theory of tides, and essentially what he does, so you have a cross section of a water basin, you have a height there, and then he rewrites everything in the analytic functions, and this is the boundary problem he gets. Now it got more famous later in the form that f minus g is parallel to phi. So this is called Riemann-Hilbert boundary value problem. Riemann-Hilbert, or sometimes Riemann-Hilbert-Privalov boundary value problem. So this plays an important role in the following sense, that what Hilbert observed, but he gave a wrong proof, and that's why it's called also sometimes Hilbert-Privalov, because Privalov corrected the mistake, but introduced another one, so it was again corrected by Aronshine some years later. So they found, so this is a boundary value problem, so they found correspondence. So the boundary value problem, so for example, if it's half space, I would just, on the boundary in Riemann problem, you tell everywhere what is the argument of f. And Riemann-Hilbert, you tell that if you subtract from f given g, the argument will be something. So basically, Riemann problem is that argument of f is equal to theta of z, and this is argument of f minus g is equal to theta of z. This relates to another thing which is just called Riemann-Hilbert problem. And Riemann-Hilbert problem is to find f in a plane with a slit so that it has a given jump. So it's a problem where you look for f such that well, basically f plus is equal to a f minus plus b on the boundary, so that the function has a given jump. And then there is a way using Schwarz reflection, if you have solution, if you have a sort of solution of this with given j and phi, to get a solution of that with given a and b, which are functions of j and phi, and vice versa. So it works only for straight lines, but it turns out, or for any curve for which you have some sort of Schwarz reflection, but this played important role in PDE and in random matrix theory. So lately it became very important thing, and so it increases the importance of the first one, because that's how you solve this one. Okay, so this problem is well known. It's called Riemann boundary value problem in homogeneous case, which we have. And our question is how to pass to a limit with Riemann boundary value problem if we don't know how. So it turns out that there is no literature about it whatsoever. So we want to reduce it to a case we know. So we want to reduce to Dirichlet. So the end of the remark, to pass to a limit in the discrete setting, we want to reduce to the Dirichlet problem, which is what we know much better. And this is how we reduce in this specific case. F is proportional to 1 over square root of dz. It means that f squared is proportional to dz. It means that f squared dz is real. So it means that if I write imaginary part of integral of f squared dz, then it will be constant on the boundary. So it's constant on the boundary. Again, it's constant on the boundary on these two arcs, because we use that when we follow these arcs. Our winding and f are coordinated nicely, but it jumps over a and b, because if you look at what happens when you go here or you go here, it's clear that winding is wildly different around this point. On the right it's plus pi, on the left it's minus pi, or the other way around, on the left plus pi. So there is a jump, each h is constant on the boundary with jumps at a and b. And then the other thing, that if should f be holomorphic, then of course h is harmonic. Why? Because you take square of holomorphic function, it's holomorphic. You take primitive of holomorphic function, it's holomorphic. You take imaginary part, it's harmonic. So basically, in the continuum setting, you can reduce your Riemann boundary value problem to Dirichlet boundary value problem just by integrating the square. So the question, how to do that in the discrete setting. So in the continuous, it's very easy. You can square homomorphic function, you get homomorphic function. Now in the discrete setting, it's not true. Well, generally it's not true. I mean, there are a couple of functions which have this property, but for generic function it will be false. So basically we want to get a definition of H similar to this one in the discrete setting. And then check that it is harmonic and check that it has these boundary values. So the problem which we have is that in the discrete, f being homomorphic doesn't imply that f squared is homomorphic. So if I just write discrete analog of that, I might run into some trouble because I will write integral not of a homomorphic function but of just some function, and the question is whether it will be well defined to start with, and then whether you get something harmonic. So the obvious answer is a priori no. It can hold only in some approximation. So we have to do this approximately and show that the error terms are small. Okay, so is it clear? So yeah. So the continuous thing is very clear, and the reason why we are doing this again is that we want to solve a boundary value problem, and we want to pass from discrete to continuous, and there is a canonical way to do it for Dirichlet problem, which we have seen. There is no canonical way to do it for Riemann problem, but in our case it can be reduced to Dirichlet, so let's reduce it to Dirichlet. Okay. So I will define the function h. And I will cheat a little bit. I will write away the definition. If I go back a little bit to this picture, so if we have discrete analytic function f which is defined on some lattice, then its derivative or primitive are defined on the dual lattice usually. So h should be defined at the centers of the squares. And normally you would want to define h at the centers of only black squares, because if I want to get it black and white, you see between black and white square, f is defined only imaginary part to only real part. So if I jump from here to here and try to integrate f, I integrated not f but only its imaginary part, and from here to here only its real part. So it's sort of, if you want really literally word by word write this definition, you can do this on the black squares easily. So you just, when you jump here, you should add to the value of h imaginary part of f squared dz, where f is taken at this vertex. And then you can do the same thing on white part. But it turns out that for the proof, for technical part of the proof, it's better to cheat and define it both on black and white, which not clear, which a priori is not clear that it's going to work, but it works better. So we'll do the following definition. So let's say a definition. So let's in our domain. So let's let this be point B. So let's define h on the centers of squares. And first we said that h at this point x. So x is the point below B. So here is the point x, and here h is equal to h of x is equal to 0. Because we'll be defining it as an integral, so we need some reference point from which we start integrating. And now I had this covering, so how was it covering? Yeah, so this is a black square. So if we have two neighboring points, A and B, not A and B we already had, U and V, and one of them is black, so for neighbors U and V, and U is white and V is black, we set H of U minus H of V to be equal, so there is an H between them, so we set it to be equal to absolute value of F on the H squared. So that a priori doesn't quite look like what we should put here. We should put F squared without any absolute value, and we should put imaginary part of F squared times dz. And we just put absolute value. But it turns out that actually it's all taken care of by two facts. I mean, first, F on every, for example, on every horizontal edge, F is either real or imaginary, so absolute value of square is just the square. And then, for example, when I go from here to here, I increase because I go from black to white. From here to here, I decrease because I go from white to black, so I put minus. So, for example, if I jump from here to here, first I increase by F squared, and then I decrease by F squared. So there are actually signs built in here, which turn out to be exactly the same as we need here, so we'll check it later. But before I need to prove a lemma, so let's say lemma 3, that H is well defined. So the problem with all such definitions is when we try to integrate something. So the problem is that the definition is unique, that if we arrive to the same point by two different paths, that we get the same answer. So proof. So we need to show that sum of differences for two paths from U1 to U2 coincide. So if I have two different paths which go from one point to another, so for example like this or like that, then the sums of the difference will coincide. And this is the same as that the sum around any loop is 0. So sum around a loop is 0. It's the same as the sum around a trivial loop is 0, the easiest one. It's the same as saying that the sum of differences like that is 0. So sum around a sort of smallest loop, a size 1 loop, is equal to 0. Now, what on this picture, if we denote again these edges west, east, north, and south, and then we have some black and white coloring, for example, it could be this one or the opposite one. So on the picture, what do we get? So we increase when we go from black to white, so we get f of east absolute value squared. Then we decrease when we go from white to black, so it's minus f of north squared, then again we increase, then again we decrease. And the question is whether we arrive at the same place. Or if we put two negative numbers to the right, the question is whether f of east squared plus f of west squared will give us f of north plus f of south. And that essentially is a Pythagoras theorem, because what we know about these points, we know that west and east are decomposition of a vector in a basis of 1 and I, and north and south in lambda and lambda inverse. If you take sum of two squares of two coordinates, you could just get the length of the vector by Pythagoras. So this is just f of z squared. So it's just f of z written in two different bases, z being this point at the center. So H is well defined. Which is already a big help, because normally, I mean, we haven't shown yet that what I'm doing is integrating f squared, but normally if f is discrete holomorphic, f squared is not, so normally you cannot integrate it. It doesn't have a unique primitive, so it's not a closed form, as they would say. So it shows that here in our setup, with our definition of discrete analyticity, it is a closed form, f squared, so you can integrate it. So it's a slightly different if from the usual definition. If you just take the usual definition, it won't work. So we have some additional information which makes possible to which makes this possible. So it's, or I mean, you can do it with usual definition if you look at it properly, but so it's sort of we look at it in a proper way. Okay. Now the second thing is, what are the boundary conditions? Lemma 4. So if this is AB, so H is equal to 0 on the arc AB, and H is equal to 1 on arc BA. So maybe if I redraw again this picture. So basically H is equal to 0 at these squares, which are immediately outside our domain, and it's equal to 1 at those squares. So it has a very nice Dirichlet boundary value problem, satisfies very nice Dirichlet boundary value problem, the one which we already studied at length. So it's, if H were harmonic, that would have done it. So we started with H of x, x being this point, by definition. Now, what happens along the arc? The boundary arc. So if we travel along the boundary arc, and suppose we have 2 points, let's say x1, x2, so it's all colored in black. And I would denote these two edges, let's say E1 and E2. And I denote this point, let's say Y. So H of x2 minus H of x1 just by definition, we go from x1 to x2, we go to y, and then we go to x2. So when we go to y, we go from black to white. So we do what? We increase it by f of e1. So it's f of e1 squared. And then we go from white to black, we decrease. Minus f of e2 squared. But what is f of e1? F of e1 is the expectation that e1 belongs to our curve with some complex weight, and then we take absolute value and square. But the complex weight in the usual setting inside the domain, it can be, for example, +1 or -1, depending on how many turns we make. But on the boundary, it always has the same sign, because on the boundary, we always make the same number of turns. So it's always same sign or same argument, because we're on the boundary. So we can factor it out. You can factor it out, and when you factor it out from absolute value, so it's just expectation that, well, E1 belongs to gamma squared minus expectation that E2 belongs to gamma squared. Or maybe I just write probabilities that E1 belongs to gamma squared minus probability that E2 belongs to gamma. But these probabilities, they are the same, because if you take E1 into your perimeter, you are forced to take E2. You cannot do anything but go through. Because if our perimeter ever wanders here, it has to go through both of them. So that does the job for one arc. That does the job for the arc AB. Now, because we started with this cell, and then we can propagate just by checking that it is constant. Now we have to jump to this cell. So let's say that, so this was point X, and let's say this point Y, which is above. Now, so this we did arc AB. So along the arc. So now h of y is equal to h of x plus f of this original HE. The original HE. So, oh, well, maybe it was denoted by B. So plus f of B. Now h of x is 0. And f of b, I claim that it is equal to 1. Why? Because it's expectation, essentially, of probability that b belongs to gamma times the weight. Weight is always 1, because we haven't made any terms. And b always belongs to gamma, because that's where the gamma starts. So it's equal to 1, which does this point, and then again we propagate, and we are done.
Why we could just skip the
one line above, because since the winding is always the same, then what I can do is I can just write that. So if you have an expectation of, well, okay, so it's the usual thing about triangle inequality. So I cannot write expectation of W equal to expectation of absolute value of W. Obviously, for example, suppose W is real. When can I write it? When W is always positive. So inside, we cannot do it, because if we have a real h, it can be either odd or even number of terms, so it will be positive or negative. On the boundary, if it's a real h, for any real h, the number of terms is fixed. It's the same as the number, so it's always positive or always negative. And if a function is always positive, this holds. If it's always negative, it also holds. So it's because basically because on the boundary expectation of whatever this times w is equal to expectation of this times, because on the boundary it's always collinear. It's always with the same, exactly the same argument. So it's okay. And then, so before we go to the break, so it's so essentially what we did, we already constructed h, which is well defined, and now we'll have to check that it is harmonic in some sense, or almost harmonic in some sense. But before that, we also need a lemma that it's actually what we want to. So it's so that it's imaginary part of f squared. So let's say, so it was lemma what, 4, lemma 5 then. So if we have two neighboring points which are of the same color, let's say black B1 and B2, and then there is point Z, there is this vertex Z, then what I want to say that h of B2 minus h of B1, so I want really to be the integral, imaginary part of the integral of f squared. So what I want to show, to say that this is indeed imaginary part of f of z squared. And then I have to put dz, which in this case is b2 minus b1. So times, so how do I put it? b2 minus b1, or absolute value b2 minus b1. Because so far we weren't really writing integrals, we're just writing discrete sums. So we just increase h by the value of absolute value of f squared. Of course, if we want to pass to integrals, we have to multiply by u minus v. So normally we have to multiply, if we want to pass to integral, we want to multiply by the mesh. So I haven't done it, so thus I'm dividing it here by the mesh. Yeah, I hope I haven't lost any square root of 2, but we'll see it in the proof. So we'll do proof after the break, but essentially what we know, if we know f of z, we know f of north, south, west, and east, and then we can calculate what are the differences. And it turns out that it's exactly this formula. So let's have a break. Well, let's. I mean, there are two different situations which we can get. So I will try to do the calculation. So there are two different situations we can a priori get in, so that the weights are 1, I, and lambda inverse lambda, or it can be a point where it's 1 on the left, I on the right, but this doesn't matter, it's just sort of rotation of it by 180 degrees, so the same formula would apply. So just B2 and B1 will be perturbed. Now, if we have here, so let's say set f equal to f of z, then what do we have at those points? So here we have real part. So real part is f plus f bar. Now here we have imaginary part, well, times I, so it's f minus f bar. And here we have projection on a lambda line times lambda. So it's here, it's not imaginary part, it's imaginary part times I. And similarly here, projection on a lambda line times lambda. So this would be just f plus lambda f bar, and this is f plus, f plus lambda squared f bar, and this is f plus lambda bar, lambda minus 2 f bar. So basically, wherever, if we have on an H projection on vector alpha, then on this H we have f plus alpha squared f bar. So this is an easy calculation, because what is a projection on alpha? Projection on alpha is a real part of f over alpha, and then we multiply by alpha. So it's alpha that, so it's alpha times f of alpha plus f bar over alpha bar. Yeah, probably I have to multiply everything by 1/2. Yeah, so it's, yeah, everything has to be multiplied by 1/2 because the real part is this over, so everything multiplied by 1/2. Yeah, and if I write that, then what do I have? I have f plus alpha over alpha bar f bar, and since alpha is a unitary number, then alpha over alpha bar is just alpha squared. Okay. And well, since lambda squared is minus I, yes? No, minus I, then we have just this written. So what we get is h of b2 minus h of b1. In this case, it's what? It's well, we go like this and like that. So this is a black squared. So from white to black we decrease, from black to white we increase. So it's f plus f bar squared minus f minus if bar squared, and well, we have to multiply by 1/4, square of 1/2, which was there. So it's 1/4, well, square of absolute value is, well, this is a real number, so it's just squared, so it's just f plus f bar squared. Now, square of absolute value is the number times its complex conjugate. And we can open the brackets, so it will be f squared plus f bar squared plus twice f bar minus f bar. Now, so this is this. This term is minus I, so it's plus I f bar squared. Now, this term is if minus if squared. And now this term is I minus minus, so it's minus f bar. So f bar cancels out. And what we basically have, 1/4 of 1 minus I f squared plus 1 plus I f bar squared. Okay, so actually I will get there a factor of 2, I think. Yeah, so it's so now maybe it's easier to just start from the other end and look what we are supposed to get on the other end. On the other end, we're supposed to get imaginary part of f squared times, and this vector in this case, this vector is 1 plus I. So strictly speaking, I have to divide it by its. So this was left-hand side, and the right-hand side is imaginary part of f squared times this vector. So obviously we can write anything in that form. So imaginary part of okay, so what do I want to do? So imaginary part of f squared is just f squared minus f squared bar over 2I. So this is the imaginary part of f squared. Or maybe where I would do the whole thing. So imaginary part of a number is number minus complex conjugate divided by 2I. So that is f squared 1 plus I over square root of 2 minus complex conjugate 1 minus I over square root of 2 divided by 2. Yeah. And either we'll get there or we won't get there, or we'll screw it up. Yeah, I think I got everything rotated by 90 degrees. Let me think. It's imaginary part, b2 minus b1. Because, okay, yes, yeah, I should indeed, I should probably put I here, that it's. So if I put I here, then this would be a vector 1 minus I, and then it would be 1 minus I minus a bar 1 plus I squared. Wait a second. So Peter Lux famously said never differentiate in public. So it's when you do complicated computation without looking at your notes, with positive probability, it gets screwed up. Maybe I would just don't start with right-hand side. I would just see where we will arrive if we'll do it that way. So it's basically, what do we have here? We have here, so I got real part. Okay. So what I have here is basically a real part of 1 minus I f squared divided by 2. Yeah, that's more like it, because this is 1/2 of that's 1/2. So it's real part of 1 minus I f squared divided by 2. And real part of something, it's imaginary part of the same thing multiplied by I. It's wrong. It's chain of equalities, which works if you write it left from left to right, but not right to left. I don't know why. So it's now we are okay. So it's imaginary part of f squared times 1 plus I divided by 2. And yeah, that's exactly what we have there. Yeah, 1 plus I divided. So the only basically yeah. So we are there. So in our case, this is 1 plus I divided by square root of 2. So this is essentially a question: do we use as lattice mesh? Do we use as lattice mesh this distance or this distance? So they're different by square root of 2 factor. So I normalized here. Yeah. So it's, let me say, yeah. So that's the statement. Yeah. So that's the statement. So we got this statement, but addition of factor 1 over square root of 2, which is not important. If we integrate, it might disappear. It sort of depends on what we declare the lattice mesh to be. Okay. Now I didn't go right the other way around. Because I forgot to multiply by I. Yeah. So imaginary. Yeah, I forgot. Yeah. Okay. Yeah. Now I see. 1 plus I. Yeah. Okay. So that's the lemma. So essentially what we accomplished so far, we have constructed a primitive of f squared. So it's indeed possible to construct. So obviously, since f squared is not in generally holomorphic, we cannot just integrate f squared. But it turns out that imaginary part we can. So it turns out that we cannot construct real part of integral of f squared, but imaginary is well defined. And it has exactly the boundary values we want. And now what we want to show that h is harmonic. Of course, it cannot be harmonic, because if h is harmonic, then if h would have been harmonic, f would have been f squared would have been analytic, and it's not the case in general. So it means that what we can hope for, that h is approximately harmonic, and it turns out that this is the case. Now I will just state a lemma which requires a similar computation. Yes?
Is it true that up to now we used only this strict version of the Riemann and nothing else?
No, nothing else. Yeah. So we only used this. No, I mean up to now we have not used any knowledge about the model whatsoever. So we used only. So the only thing we used about the model, that if we sort of do this transformation, the weight changes by square root of 2, and square root of 2 goes nicely with 1 plus I over square root of 2. So this is so that's the only thing we used, and then we get this nice analyticity where we have projections on 1I lambda inverse lambda. In principle, if you have any discrete analytic function which is defined on the vertices of this lattice, what you can do, you can draw a lattice which shifted by half, put lambdas and lambda inverses here, put projections, and then you would get the same definition which works well. So far we haven't used any knowledge about the Ising model whatsoever, except for purely combinatorial definition. And in principle, one can avoid using any knowledge, but that's not what we are going to do. So there is the next lemma. So as I said, H on black and white is slightly, they're slightly different. So H on black, so far what we know that H on white is always bigger than H on black. So for two neighbors, H on white is always bigger than H on black. So for neighbors, it's just by definition. H white is bigger than H black. Because when we go from black to white, we increase. When from white to black, we decrease. So if you traverse from 0 to 1, here you go up, down, up, down, up, down, up, down, and eventually you get to 1. Now, the question is, so we have, it's more logical to consider just H white or H black, but we have to do two of them because one gives us 1/2 of boundary values and another gives another half of boundary values. So now there is a very nice observation that if we take H on black and we compute Laplacian, and here we can compute Laplacian not compared to white, that won't do anything, but we compute Laplacian to black neighbors. So the Laplacian of H on black is positive. Wait a second. So blacks are smaller, Laplacian is negative, yeah. Negative. And Laplacian of H on white is positive. So let's say black Laplacian, white Laplacian. So a small remark, what does it mean? So let's roughly think of a crosscut of a domain. So remark, so what do we have? We start, so we have black, white, black, white. We start on black, and we start at exactly 0, and we end on white, we end exactly at 1. Now we go up, down, up, down. Now what happens? So what does it mean if a function is if a function has so what does it mean if a function has positive Laplacian? Essentially, it means that it is a convex graph. Sort of, yeah. So it's, well, one-dimensional analog, if we would have had it just in one dimension, would be exactly convex. So basically what we get that the white graph is a convex graph which ends at 1. And black graph is a concave graph which starts at 0. So more or less, yeah, maybe I will just draw a more illustrative picture. So it goes something like that. So if you take the exact values, so they will be sort of you go up, then you go down, then you go up, then you go down, then you go up. So it didn't work very well. Let's see. So essentially, this is also goes the nice way around. It could have been the other way around, and then we would have had two functions which might be very different in the middle. But here in the middle, they are closer than on the boundary, because one is concave, one is convex. So essentially, the maximum of the distance will be on the boundary. So if we want to show that these two functions are close, it's enough to estimate on the boundary. So in a sense, so it's so supremum of H white minus H black of our all neighbors is attained on d omega. And it's also nice because if, for example, I take harmonic functions with the same boundary values, if I take harmonic function with the same boundary values as, so if this is H, let's say H white star, which is equal to H white on boundary and harmonic. So the real analog would be just linear function. So it's bigger than then bigger than H white. On the other hand, if I do the same thing with H black and I take harmonic, it will be smaller than H black. So basically we have a sandwich. We have two harmonic functions. In between them we have this subharmonic and superharmonic. So in a sense we are almost there. If we show that the distance is small on the boundary, then they will be just squeezed between harmonic functions which have boundary values. One has boundary values 0 and 1 minus epsilon, and another has boundary values epsilon and 1. So it will be squeezed and everything will be nice. So essentially, yeah, that is the remark. Yeah, maybe I'll return to lemma 6 a bit later. Oh no, let's deal with the let's put aside lemma 6 for the time being and just continue this line. So let's say set H discrete harmonic and HW star equal to HW on the boundary. And the same HB star so just solutions of the Dirichlet problem on the boundary. Then we get that HB star is at most HB, which is at most HW, at most HW star. And this because it's harmonic. This one is superharmonic, so it's bigger than harmonic. Now this is by definition smaller than this guy, so this is by definition. This is because superharmonic is bigger than harmonic, and this is smaller than harmonic. Now, let's say lemma, what was it, 7 or, yeah. So away from A and B, so if we take our domain and we take away some neighborhoods of A and B, HW star minus HB star tends to 0. As mesh of the lattice tends to 0. So basically, if we take some domain omega and we approximate it by lattice domains omega delta, and we take smaller and smaller mesh, then outside these 2 points, the difference of our functions goes to 0. Well, it can't go 0 everywhere because near B our function jumps by 1, so it's harder in the neighborhood. But if we cut neighborhoods away, then it goes from 0. Now, so this is the tricky part. So this is the part where I will cheat a little bit and do non-self-contained proof and use the properties of the Ising model. Now, in principle, it obviously doesn't follow from this inequality. Obviously, can have functions where difference doesn't tend to 0. And obviously, we can have subharmonic and superharmonic functions, or even exactly harmonic, so that the difference between them stays equal to 1 over 100. Now, if we want to deduce it from what we know, we have to, we actually can. One has to do some more precise version of Lemma 6 and check the derivative estimate. So in principle, it is doable. In principle, one can do estimates of this. And, well, maybe we'll do it next lecture. So I'll do a proof. So this is the only place, essentially only place we use something about easing. So the difference of those two functions, so supreme over omega, is no more than the supreme on the boundary of omega. Which essentially on the boundary they're equal to the usual functions. So it's just supremum of h double minus hb on the boundary of omega. And what is the difference of h at two neighboring points? So it's supremum over the boundary of omega of a function f. Supreme over boundary of omega, that probability that E belongs to our curve gamma. Now, I mean, that of course is equal to 1, because we know that at the starting point it belongs to 1. But what I will do now, I will only okay, so I will only prove it away from A and B, which I intended. Now, so basically, well, there is a fork here. So there are we use two different estimates. So in these neighborhoods, on the boundary, we use estimates that our function is no more than 1. So here we use that the function is no more than 1. And elsewhere, we show that it is very, very small. Now, if you have a harmonic function which has boundary values no more than 1 on very small intervals and very small elsewhere, inside it will be very, very, very small away from these intervals. So if I make function go up to 1 here, it only will influence a small neighborhood of it. So it's not only sort of neighborhood compared to the size of this guy. So that's what we do. So now let's do it away from A and B. And away from A and B, what is it? It's a probability. So this is a probability, for example, at this point, it's a probability that our curve passed through this point. It's a probability in the FK model that, so what was our picture? Our picture was that there is this cluster, and the probability the curve passes here is the probability that this point, E, is connected to the bottom by a cluster. So it's exactly this probability. For our interface to pass through this point, we need the cluster to go all the way up. Which is the probability in the Ising model, where I have boundary conditions plus on the bottom and free elsewhere. is the probability in the Ising model, in these boundary conditions, that spin of E is equal to plus minus 1/2. So it's kind of magnetization is the same as this usual high-low temperature calculation. So it's a magnetization which this plus boundary creates. So how more likely the spin is being plus if the upper boundary plus. So we use the only bit of information about the Ising model that if you have a large box and you magnetize one part of it, it doesn't propagate at criticality. So it's a critical Ising. So it's, let's say, TC Ising. So we use something which was calculated by Anzager, or it has been calculated many times since. So we will only use this bit of information. If we have very large discrete domain, we put boundary conditions plus on the other side. It doesn't influence things elsewhere. The influence is very small. It decays as a power law. So it's small. So this basically tends to 0 as mesh tends to 0 by Anzager. So that's essentially the only thing we need. It's also the same thing for point inside. The probability that our curve passes through inside point also can be written as a magnetization, estimated by magnetization here, so it's also small. So our curve is not space filling. So that's the only piece of information we use. One can view it as a black box. There are two alternatives. One goes and read those all papers and sees how people proved it, or one can actually prove it from what we have done up to now, or one can give a new proof. So it's kind of a percolation was played by Russo, Seymour, Welsh. So these arms exponents, they were telling us that perimeter is unlikely to go through a given place. So here we need Russo, Seymour, Welsh for the Ising model. So there is actually Russo, Seymour, Welsh for Ising model. So there are papers of Hugo and Hugo, Duminiu and Clement Angler, and so there is a number of ways to do it. So there is one can also do. Yeah. So maybe I will just write it that it's Russo, Seymour, Welsh for the FK Ising. And now we actually have Russo, Seymour, Welsh for most FK models, so it's kind of follows from other things. Okay, so let me maybe then kind of wrap it up, model Lemma 6. So where we are. Yeah, okay, so. So wrap up of this thing. So as mesh tends to 0, the difference between these functions tends to 0. Which means that there will be, which means that all these four functions, h black and h white and h b star, h star, they tend, as mesh goes to 0, to function h, which is h is harmonic, h is equal to 1 on the top arc, and h is equal to 0 on the bottom arc. Now by convergence, I mean it's convergence inside omega away from A and B. Because I have a function which has boundary value 0 on the bottom, boundary value 1 on the top, so near these points it's rather discontinuous. So if I take away the neighborhoods, it will just converge uniformly and nicely. So let's say converges uniformly. And it doesn't pose any problem that I take away the neighborhoods because our function is bounded. So whatever happens with bounded harmonic functions in small bow doesn't really concern us. If we had a pole, this could have been different, but we don't. So it's. Now also what we have that gradient of h is equal to imaginary part of f squared. What was it? Imaginary, yeah, more or less like that. So the derivative of h in the direction, say tau, is equal to imaginary part of f squared times tau. And I think there was a 1 over square root of 2 in front. Or rather, it's like h of x plus tau minus h of x, something like this. Well, now what we can do, we can either prove that from convergence of h we can imply convergence of derivatives, which is a bit tricky because our functions are not harmonic, so they can oscillate a little bit more. Convergence of derivative is easy for h star and h star, so one has to do that. Or alternatively, we can observe that we just integrate, and we get that well, primitive of h is equal to 1 over square root of 2 imaginary part of, no, not sorry, h. Imaginary part of integral of f squared dz. And now what when we do this, we actually, in the discrete level, we have to sum the things. So we sum the things, and let's say, so this is our lattice. This is the mesh delta. So when we sum the things, yeah, maybe let me, before I write this, I'll sum the things. So we have, when we start summing from one point to another h, we have, let's say, h of y minus h of x is the sum of such sums. It will be sum of sums here. So it's 1 over square root of 2 imaginary part, sum of f squared of xj tau. Now, this is the Riemann sum if we multiply it by lattice mesh. And in this case, lattice mesh is delta times square root of 2. So it's basically times delta square root of 2 and divided by delta square root of 2. So it's 1 over twice delta. And this is Riemann sum. So it's sort of discrete version. Let me just write that this is discrete. So I write delta integral, imaginary part of the discrete integral of f squared dz from x to y. And then we pass to a limit. So h converges to h small of x minus h small of y. Will then be equal to imaginary part integral of f squared dz, where f squared over delta will converge inside omega away from AB to the point f squared. Let me just move 2 to the other side. So I think I will stop here because we'll discuss it more next week, because this is informally what happens. But formally, we have so there is one subtle point. It's not that f squared converges to something, but f squared divided by delta. So because you see in this formula h nicely converges, and here f squared is divided by delta. So f squared itself is of the order delta, and we gain this delta from integration. So f squared itself, it converges to 0. So we have to divide it by delta. And this division by delta actually will generate something interesting. If H is a solution of Dirichlet problem and it's conformally invariant, when you map to a domain, it maps by the map. F will be conformally covariant. So f squared will be conformally covariant. It will be multiplied by derivative of a map. And f will be multiplied by square root of derivative of a map. And also to pass to this limit, there are 2 ways to do it. So one I said is just to show that derivative of h has limits, but that's a bit difficult. If we proceed otherwise, we need to use some precompactness, like for percolation. We need to show that there are subsequential limits, and then this identity will do the job. So basically, we stop here, and tomorrow we'll, in a week, we'll discuss in detail this convergence and the 2 things which I have to do to depths is one, to show that there is some precompactness of f's, and the other is lemma 6, why it's subharmonic and superharmonic. Okay, so till next week.